This is part 3 of the lecture on classical wave mechanics. The Dirac equation we've shown can describe waves in an elastic solid, and the equivalent equation describes elementary particles that are fermions, such as an electron. So the general linear Dirac equation has a partial time derivative, has a convection term involving a gradient and a wave velocity operator, and then also has an imaginary term which will drop out when we start computing observable quantities. Okay, for an electron, this operator has the form of mass or frequency multiplied by a matrix gamma 0, which we've shown rotates the wave velocity. Okay, we can take that wave equation, multiply by the Hermitian conjugate, stick a factor of I in there, and we can get a Lagrange density, which would have this form. And similarly, we can get a Hamiltonian density. And then we can take those and compute the wave momentum and the wave angular momentum are computed from the Lagrangian. And then if we add the intrinsic angular momentum and momentum, we would have these two expressions. Okay, so the total angular momentum of the wave and also the medium carrying the wave, that's the same as in relativistic quantum mechanics. And the momentum density has an extra term that most people would not be familiar with, but it's been shown that this term is necessary to make the energy momentum tensor symmetric, which is typically a requirement for general relativity. So suppose we have two of these waves and we want to add them together. So we have waves A and B, we add them together and we calculate the spin density, or in this case twice the spin density. Okay, what we get is the value for wave or particle A plus the value for particle B. But then we also have these interference terms, which really should not be there, because really the spin densities should just add together. Okay, so if we force the interference terms to be 0, and in particular if these waves are eigenfunctions of one of the components of spin, so that the matrix character of it drops out and we just have some constant, then we would get the Pauli exclusion principle that says that these wave functions must anti-commute. So that's the same as saying that the interference terms would cancel. And then the way we force this to be 0 is by introducing phase shifts, which we call interaction potentials. So the interaction potentials are put into the wave functions in order to force the interference to cancel. So let's suppose we have a electron wave function, and let's normalize it to 1, which means we factor out a factor of h bar. The phase shifted wave would have to satisfy the free particle equation. Okay, so this would be 0. And similarly, and we can calculate a Hamiltonian from that if we want to, but I'm going to look at the force density. So again, because the phase shifted waves are independent, there would be no force on the phase shifted wave. And force would be the total time derivative of the momentum density, in this case the wave momentum density. So what I'm going to do is solve this equation that says that there's no force on the phase shifted wave. Okay, and make some definitions here. We'll say there's a wave density, a wave current, or current density, and we're going to define the vector potential according to this equation, where it's proportional to the gradient of the phase difference, phase shift. And we make one more assumption, which is that the phase factor varies much more rapidly than the wave density, which is like the amplitude. So the phase varies much more rapidly than the amplitude. That's similar in quantum mechanics to assuming that your incident wave is a plane wave. Okay. So the force density, if you work that all out, ends up looking like this, where you've got a time derivative of the gradient of the phase shift, and then you've got this curl, this cross product with the curl of the gradient of the phase shift. Okay, the curl of a gradient can be non-zero in this case because phase shifts are multi-valued functions. So this is an example of what's called the Weil gauge or the temporal gauge. If we define the magnetic field as the curl of the vector potential, the electric field as the time derivative or negative time derivative, we can actually decompose that using Helmholtz decomposition into a gradient and a term which is a curl of something else, call it A prime. Then if we make those substitutions, we would get the Lorentz force. So you've got the electric field here, and then the velocity operator cross with the magnetic field. Okay. Now, using those definitions, we have an interesting property that because the magnetic vector potential is defined as a gradient of a phase shift, if that phase shift is unique within a multiple of 2 pi, which would be what you would normally expect, then the magnetic flux is quantized. So using Stokes's theorem, you can convert the flux into a line integral around the azimuthal direction. So this just get a factor of 2 pi times the radius in here. Just a factor of 2 pi. And then that's quantized where n is the multiple of 2 pi that you had. So you get n pi times h bar over the charge. So that is the magnetic flux quantum. We could also suppose we have a different phase shift. In this case, suppose it goes like m phi minus omega t. So this is maybe coming from some kind of spherical harmonic or something. And then divide that by the radius with some normalization factor there. In that case, if we put the azimuthal mode number as a half, we would have the electric field of a point charge, and the magnetic flux would be actually the same as you would get for the electron, the flux in the z equals 0 plane. Okay. Furthermore, if we take that Lagrangian for the 2 electrons added together here, these are symmetric between A and B, but I took the interaction term and stuck it separately here. So each of these terms actually it just is 0 because it satisfies the equation. So what I'm going to do is take the second electron, B, and replace it with, instead of having the electron wave current here multiplied by the potentials, I'm just going to put the ordinary charged currents in here. So I'm replacing the electron with the electromagnetic fields. Okay, but they still just add up to 0. Then just using some identities here, I can convert that to this expression, which is very similar to the Lagrangian density of quantum electrodynamics. The one difference is this factor of a half. And normally in quantum electrodynamics, when varying the potentials, you hold the currents fixed. but actually they're functions of each other. So when you do that, you really should get, if you're going to hold it fixed, you need to get rid of the factor of a half. Normally you should vary both of them. So getting rid of the factor of a half gives you the Lagrangian density of quantum electrodynamics prior to quantization. So for a single electron interacting with the electromagnetic field. Okay, so summary of part 3 is that wave interference yields the Pauli exclusion principle and the interaction potentials. Magnetic flux quantization results from the magnetic vector potential being proportional to the gradient of a phase angle. The proposed relationship between the electric field and magnetic flux is consistent with the properties of an electron. And the Lagrangian density is similar to quantum electrodynamics. And the overall summary is that classical wave mechanics is a good tool for modeling the wave behavior of matter. And secondly, the decomposition of elastic shear waves into interacting particles yields dynamics similar to relativistic quantum mechanics. Okay, and here's a list of publications and my website. All right, thank you for your attention.